All right, welcome to Material Science and Engineering. What I'd like us to focus on today is calculating these three values, the lattice parameter of copper, given its atomic radius and the fact that it's face-centered cubic. And then I'd like us to calculate the atomic packing factor, and finally the theoretical density of copper. So let's get started. So I'm going to begin by just drawing a unit cell for copper and indicating, as the problem has told us, that it is face-centered cubic in terms of its crystal structure. So FCC stands for face-centered cubic, and the name describes exactly what it is. Cubic means that the edge lengths of the unit cell are all equal to each other. That is to say that width is equal to its depth here, which is equal to its height here. So all of the cube lengths are equal to A. Excuse me, I'm going to write A there. And the fact that it is face-centered cubic means that there are atoms at the corners of the lattice. So I'm only going to draw the lattice points. I'm not going to draw them large because then they'd be too hard to see. But being face-centered cubic, in the middle of this face, the one on the right-hand side, I'm going to slightly cross-hatch it so you can see it better. There's going to be one atom there in the center of the face. Similarly, on the let's try looking at the bottom side. There's going to be an atom in the middle of its center. And now I'm going to stop trying to sketch each face because it'll get too complicated for us to see. But there's going to be an atom in the center of the left face, an atom in the center of the back face, an atom in the center of the top face, and an atom in the center of the front face. That's the one that's hardest to see of all. And so there's front, back, left, right, top, bottom, 6 faces, right? And each of them has, an atom, and then there's 8 corners, each of which has an atom. And while I'm here thinking about that, because we're going to need this for later, of these 6 faces, how much of that copper atom is inside the unit cell? And so if I'm going to concentrate on the top part here and maybe even go to a shaded marker. So if I were to draw this atom kind of more like its size, which is really impossible to do in this little thing, but if you can strongly apply your imagination and kind of envision it in terms of, I don't know if you can or not, but if not, go to a kind of Google face-centered cubic and look at some good images. But half of that atom is inside the unit cell. And so of those 6 atoms, with half of them being inside the unit cell, we end up with 3 atoms from the faces that are inside the unit cell. And of these 8 corners, so I'm drawing an arrow to a corner, we got 8 different corners. And this is harder to see unless you sketch more of the crystal, and I encourage you to, kind of Google this a little bit, but they're shared by 8 other unit cells that touch at that point. And so you end up with 1 atom from all those corner positions. So you end up with 3 plus 1 equals 4 atoms in a face-centered cubic crystal system. So we'll need that for B, and let's just put that on hold now. And let's return to kind of our first step here. We're going to now work on part A, which is calculate the lattice parameter. In other words, find A. A is the lattice parameter. That's something worth remembering. Parameter. It's the edge length of the unit cell. Find A in terms of R, right? Because we're given R, we're not given A. R is the radius of these atoms. And so now what I'd like to do is pull out just the front face here. So I'm not drawing the rest of the crystal, I'm just drawing the front face. And of the front face. You know, we've got an atom in the middle of the face. We've got atoms at the corners. And now, if I draw atoms closer to actual size, you can perhaps see where touching happens, and so now I'm going to draw that center ion in terms of its actual size. And so for copper, all atoms are the same size. We know that the radius is equal to 0.128 nanometers. And so can you appreciate that touching of those copper atoms is occurring along the body face? And the fact that they touch is quite helpful to us, because that body face length, right, the length of a, if I just give it a name, L, and of course this length is A, and the bottom length is A. And so by Pythagorean theorem, we see that L squared is equal to A squared plus A squared. And so L equals the square root of 2 times A. And L, kind of by inspection, is going to equal a sum of these different, a sum of this radius of copper, that's one radius of copper, this radius of copper, so that's 2 radiuses of copper, this one, that's 3 radiuses of copper, and then that one. So this L is equal to 4R, and therefore A is equal to 4R over the square root of 2, which is equal to if I plug in that R of 0.128, we will get this following answer, 0.36204 nanometers. So that is the answer to A. Part A asks for the lattice parameter A, and the answer is 0.36204 nanometers. All right, so now for B. B is to calculate the atomic packing factor. And so that is the number of, I guess the way of expressing it is the fraction of space occupied by those atoms that are inside the unit cell divided by the volume of the unit cell. So in B, it's find APF, atomic packing factor. And so that will equal the volume occupied by the copper divided by the volume of the unit cell. And so we'll address this in part 2, which will be in the next segment.